15.2, the equilibrium constant. The reaction shown here between dinitrogen tetroxide and nitrogen dioxide is an equilibrium reaction. The forward reaction has a rate law that is equal to Kf times the concentration of N2O4. The reverse reaction has a rate law equal to Kr concentration of NO2 squared. Therefore, at equilibrium, rate F equals rate R, or the forward rate equals the reverse rate. Setting these two expressions equal to each other and rewriting it, it becomes Kf over Kr equals the concentration of NO2 squared over the concentration of N2O4. The ratio of the rate constants is a constant at that temperature, and the expression becomes equilibrium constant, or Kf over Kr, equals the concentration of NO2 squared over the concentration of N2O4. Consider the generalized reaction. The equilibrium expression for this reaction would be products over reactants, keeping in mind that the coefficients become the exponents. Since pressure is proportional to concentration for gases in a closed system, the equilibrium expression can also be written in a similar fashion. Sample exercise 15.1, writing equilibrium constant expressions. Write the equilibrium expression for K sub C for the following reactions. Using the law of mass action, we write each expression as a quotient having the product concentration terms in the numerator and the reactant concentration terms in the denominator. Each concentration term is raised to the power of its coefficient in the balanced chemical equation. So for reaction A, we will have the concentration of O2 cubed divided by the concentration of O3 squared. For reaction B, we will have the concentration of NOCl squared divided by the concentration of NO squared times the concentration of Cl2. And for reaction C, we will have the concentration of AgNH3 divided by the concentration of Ag times the concentration of NH3 squared. Please do the practice exercise. There's a relationship between K sub C and K sub P. From the ideal gas law, we know that PV equals nRT. Rearranging it, we get P equals NVRT. And plugging this into the equilibrium expression for K sub P for each substance, the relationship between Kc and Kp becomes as follows. Kp equals Kc times RT to the delta N, where delta N is moles of gaseous product minus moles of gaseous reactant. Equilibrium can be reached from either direction. As you can see, the ratio of nitrogen dioxide squared to dinitrogen tetroxide remains constant at this temperature no matter what the initial concentrations are. Here again, we can see K sub C values remaining fairly constant. This is the data from the last two trials from the table on the previous slide. It doesn't matter whether we start with N2 and H2 or whether we start with NH3. We will have the same proportions of all three substances at equilibrium.